understand the concept of vectors as it relates to forces, because we can represent a force as a vector and using line segments. All right. We're going to be able to use the resultant of two forces using the laws of vector addition. I'm going to understand something called an equilibrium, which is something I mentioned before. Equilibrium is the force, or the vector, I should say, that works in the exact opposite direction with the same magnitude as another vector. And that's going to be important for when we are trying to find something that is in what's called equilibrium, which is to say that you have a system where all the forces are balancing each other out. Right? So we'll get to some of those questions in a minute. We're going to be able to find the resultant of forces using horizontal and vertical components, all very critical parts to what we're going to be doing today. There's a homework question, and I'm hoping that I'll cover enough ground today that you will be able to get the homework question done. But let's get going. So, background information. The magnitude of force is measured in newtons. Some of you have done this already in physics, I think. But the abbreviation N is what we're going to be using to represent newtons. And the typical force, which is caused by the Earth's gravity, causes an object to accelerate at 9.81 meters per second. And the magnitude of the gravitational force is a product. So you multiply together the mass of the object. So let's say it is 5 kilograms. You multiply that mass, which is not a vector, that's, as we said, for a scalar, by this acceleration, the 9.8, and then that will become a force, which you're now measuring in newtons. So if I gave you that the mass was 5, you multiply by 9.8, and that's going to give you a Newton force that is pressing down or moving in the direction of gravity is pulling that thing. Sometimes an object is acted upon by a number of forces. And we have to find the one force equivalent to all of these forces, and we're going to call that a resultant. We've used that term before. All right, single force having the same magnitude and acting in opposite direction is referred to as the equilibrium. I just talked about that a while ago. Let's get to a very hopefully simple example to start this off. Jan is pushing on the handle of a lawnmower the force of 200 newtons. So the force that is represented by this vector pressing down into the ground, the lawnmower, has a force of 200 newtons, and it's pressing down, the arrow is pointing down into the ground. Handle forms an angle of 50 degrees with the ground. So there's a 50-degree angle right there. What's the horizontal force acting on the mower? What other force is involved, and what is this magnitude? So by that, what we're saying is that, and I'll put a line in to represent what I am talking about, is that there are, in fact, horizontal and vertical forces at play here, right? And hopefully that makes sense. When you're pushing with this angle this way, you're going to have a force which is horizontal. Let's put in, first of all, a line which has a right angle to the ground. So there's going to be a horizontal force, and there's going to be a force pushing down. So that's what's the other force involved, and what's the magnitude. These two represent the splitting apart of this 200 Newton force into a horizontal force running along the x-axis, if you will, and a vertical force, which is actually going down along the y-axis, going vertically downward. And we're asked to find the magnitude of those two forces. Okay, well, that sounds and that should look very much like a simple SOHCAHTOA question. There's a right angle here. So I should be able to find the horizontal force by just simply using the cosine. Just remember SOHCAHTOA, cosine is adjacent of hypotenuse. So let's call this the x horizontal component. Let's call this the y vertical component. The cosine of 50 would be equal to the opposite side, which is, the adjacent side, which is x, over the hypotenuse, which is 200. So this x component is going to be equal to 200 times the cosine of 50. And we're going to see this quite a bit, that when we're trying to find the horizontal component of a vector, when you take a vector and try to split it apart into horizontal and vertical component, that is just simply the vector's magnitude itself, which in this case is 200 newtons, multiplied by the cosine of the angle that that vector is forming with the horizontal. All right. So in this case, that would be cosine of 50 degrees. And, you can work that out, but that's really not what we're about right now. You can do that on your own time. So that's going to be equal to some number, right? And you can do that on your own time. So that would be the x component of the vector. The y component of the vector, right? Well, if we well, first of all, let's work out what this side over here would be. That would be losing sine. So let me just erase this. So to get the y component, we're going to say that the sine of the same 50 degrees is equal to the y over the 200. So of course, just by simply multiplying this out, then the y is going to be equal to the vector of 200 multiplied by the sine of 50. And again, you can work that out on your own time. That's not really what we need to spend a lot of time on right now, getting actual numbers, because you can easily do that on your calculator. So that's going to be some number here. And this is what I really want you to get out of it. You take a vector, you can take any vector, such as this 200 Newton vector, and you can split it up into sort of a horizontal component and a vertical component. Well, one of them is a force that's pushing down into the ground, and one of them is pushing to the right. The one that's pushing to the right, that's the horizontal component, is 200, the vector itself, times the cosine of the angle that the vector is making with the horizontal line. Right? And then to find the vertical component, we take that same vector and we multiply it by the sine of the vector that we're trying to sort of split into its two components. So again, you can finish up this on your own time, getting the actual numbers that these represent. What you're going to find in both cases is that these two vectors are going to be less than the 200. Right? Did cosine of 50 times 200. In fact, we'll just do that one quickly, and then you can do the other one later on your own time. What is 200 times the cosine of 50? Please make sure your angle is, or your calculator is in degrees and not radians. If I could get one of you to give me that number very quickly, please. So 200 times the cosine of 50. You all should have your calculators there close by. What is that number? Give me to, I don't know, one decimal place, please. Thank you. 128.6. Thank you very much. So the 128.6, and that's of course also newtons. And notice that that's less than the 200. So even though you're pushing with a force of 200, when you split it up into two parts, each of these two parts will be less than the 200. But when you put them together, they combine to give you a force of 200. One pushing to the right and one pushing down. Okay, so I'm going to move on from there. And now we're going to, in fact, all those, you know what, I just forgot that all those calculations are right here. So here we go. I'm not going to spend more time on it here. I'm just going to move on, but you can see that the calculations are all on this page. And it's as it says down here, something I just mentioned, the horizontal and vertical forces are called components. And the result of the components is this 200 here that we're talking about. Let's move on. I know I might seem like I'm rushing to an extent, but I just know that there's quite a bit I want to get through today. So, but still, please, you know, you're always welcome to ask questions if you're not sure about anything. Okay, now let's just talk a little bit about these components. And some of you have done this in physics before, because I know when I've taught this course in the past, people tell me, oh, we did this in physics. Okay, that's great. So when we're looking at the components of a vector, right? So this vector, for instance, if we put them on a Cartesian grid, this vector is somewhere in the second quadrant, right? And it has an angle. If we were to use the angle measuring from the x-axis, positive side of the x-axis, and going in a counterclockwise direction, if we wanted to standardize this, then we could easily come up with the components of the vector by kind of doing what we just did a while ago. Take the length of the vector. So this vector has a magnitude. The one I'm pointing to now has a magnitude. And when I want to find the horizontal component, so along the x-axis here, I would take the magnitude of the vector and multiply it by the cosine of the angle. And again, use the angle that's measuring from the positive side of the x-axis all the way over to here. So obviously we know, using the cast rule, that the cosine is going to be negative in this quadrant over here, and that's fine, right? Because it will help us when we're putting all of these vectors together to know that sometimes the x-coordinate, right, is going to be a negative x-coordinate. And when I say x-coordinate here, think of the tip of this as being as having components which are x and y components, and the x component, if you're in the second quadrant, is going to be negative, whereas the y component will be positive. As long as we use this angle here, right, measuring from the positive side of the x-axis as the cosine, as when we're doing cosine, we take the cosine of that angle there. Same thing for when you want to find a vertical component. So really what we're doing is just finding the x and y components, x and y coordinates of where this ends up with a length of a. That a represents the hypotenuse of the triangle that we're forming. So the length of a times the cosine gives us the horizontal component, which could be negative. The length of a times the sine of that angle gives us the vertical component, which itself could be negative because I could be down here in the third quadrant where only tangent is positive. So in summary, if I wanted to find the components of this vector A, right, giving them as an x and a y coordinate, then I could take the length of A and multiply it by the cosine of the angle for the x, and I could find the y by taking the same length of A and multiplying it by the sine of the angle. So just think of sine as being my y coordinate and think of x as being my, think as cosine as being my x coordinate. That's the way I like to look at it. In fact, when I teach this, when I'm teaching sine and cosine to my advanced function students, I actually make that point. Think of sine as your y and think of cosine as your x. Okay, so this can help us when we're adding a whole bunch of vectors together, and I'll do an example of that shortly. Okay, let's look at this one. Well, we're going to do this in the traditional way, and then we're going to do this traditional way, meaning what we've done before, creating a parallelogram and using the length of the diagonal as the sum of those two vectors. Okay, so two ropes are attached, and then we're going to do this using components and see how they're different and how they're similar. Well, actually, the answers will be the same, but the process will be different. That's the only thing. So two ropes are attached to an object and pull with forces of 360 newtons. So that's what this diagram is meant to represent. And there's a 70-degree angle between them, all right? The forces act at an angle of 70 degrees to one another. So between them both, there's a 70-degree angle. Find the equivalent single force that would have the same effect on the object and describe its direction relative to the 300 Newton force. So let's go ahead and use the approach that we've always used when we're doing this, but with using the parallelogram law. So 360 is here, right? That 360 Newton line. Then the 300 Newton line, this is not drawn to scale, by the way, so that's just the way that is. I'm going to put that 70-degree angle inside here. Then I'm going to go ahead and put a dotted line to represent the rest of this parallelogram. Okay, and what we're trying to find, just remember now, what we're trying to find is the length of the line which represents a diagonal between those two, right? And then of course we have to figure out what the direction of that line is as well. Okay, so how do we do that again, right? Just remind me, folks, we've done this before. How do we find the length of that line? Because that line represents the sum of these two forces. Using the parallelogram law, it will be the sum of those two forces. So that's the diagonal. There's a 70-degree angle between them. Remind me how we did this in the past. Remember, we're going to do it this way, then we're going to use the components later on and hopefully get the same answer. How have we done this in the past, folks? Help me out here, please. Come on, folks, I need to get some input from you. How have we done that question in the past? 300 Newton, 360 Newton, 70-degree angle between them. I need to know the length, the magnitude, and then of course we need the direction as well. I need to know the magnitude of that line, that dotted line, which represents the sum of those two. Does anyone not remember how we did this before? How would I set this up? Right? Which of the trigonometric concepts did we use to do this? Trigonometric tools, the cosine law. Thank you, Sarah. Okay, let's move on and do that then. So remember now, we're not going to use the angle 70 degrees. We're going to use its supplement, right? Because its supplement allows us to, therefore, figure out what the length of this line is right here. So we're going to say that this 300 Newton line, right, is one of the lines that we're going to use. We're going to use this as the other side of the parallelogram as the same 360 newtons. So we're going to say, using the cosine law, that this force that we're going to call, let's call it x, right? That x squared is going to be equal to the 300 squared plus the, I'm going to need more room than that. So x squared is equal to the 300 squared, you should all have seen this before, plus 360 squared, minus 2 times 300 times 360. Get your calculators out in the meantime, please. The cosine of not 70, but 110 degrees, the supplement of the angle, okay? The cosine of 110 degrees. So Sarah is right. So let's get what x squared is, and then let's get what, actually, let's just cut to the chase here. Could one of you get your not all, actually, you should all be doing this. Can you get your calculator and work out not just x, but not just x squared, but actually work out what x is? And then we're going to talk about how we're going to get and that's x approximately equal to. And we're going to talk about how we're going to get the actual direction. It says relative to the 300 Newton force. So quickly get your calculators out for me. As I said, we don't have a lot of time today, so the faster we can get this done, the better for all of us. Sarah said use the cosine law, we set it up. Okay, did you square root that already? It looks like you probably did. So 541.7, thank you very much. And that would be in newtons as well. Okay, so hopefully everybody else got the same answer as Ashvan, and hopefully everybody is trying to work on this for themselves, get the practice. So we're going to go with the answer that we just got from Ashvan of 541.7 newtons. But we also need to know the direction of this relative to the 300 Newton line. So what that means is, I'm going to put a line here in red. Right, the 300 Newton line is this line that I'm pointing to right here. And the question says direction relative to that line. So I'm putting that in as the angle that we are trying to find, right? Now, what we've done in the past is use the cosine law to get, the sine law to get that. The truth is we can also use the cosine law. And I'm purposely going to use the cosine law this time because I want to demonstrate to you that you're going to get the same answer, right? And there's a question on your homework that requires you to use the cosine law to get an angle, a missing angle. So we're going to use the cosine law this time. So let me quickly show you what it is that we're going to be working out. Let me draw another little triangle over here, similar to the one that we're working with now. All right, this is 300 here. This is 360 right here, right? I'm just kind of following the pieces of this triangle over here. And this side that we just worked out is a 541.7. All right, these are all in newtons, by the way, but we're using the magnitude to represent the force in this particular case. By the way, I'm assuming that everybody else tried this like Ashvan and got the same answer as Ashvan as 541.7. I'm going to make that bold assumption that people tried this for themselves and got the same answer. Is that reasonable? I haven't worked this out for myself. Did you all try this? Okay, Sarah says yes. Okay, perfect. So if I want to use the cosine law this time, I'm going to remind you what angle we're trying to find. We're trying to find that angle inside here. You can use the cosine law to find a missing angle if you have all three sides. We do have all three sides. We have the 300 Newton side, this side right here, or the 360 side right here. We have the 541.7, which we just figured out right here. And we're trying to find this angle between this side and the 300 Newton side. So here's how this works. When you're using cosine, the cosine of the theta, we'll call this angle theta. The cosine of theta will be equal to the two sides that are around the theta. So 300 squared plus the other side which is around it, to the 541.7 squared, minus the side that's across from it. So across from theta is the 360. And all of that is over 2 times the 2 that you added together, 300 and the 541.7. Okay. Now I should let you know that occasionally this thing that you're working out turns out to be negative. And by the way, thank you, Sarah, and thank you, Javier, for having confirmed that answer for me. This thing works out to be negative. Sometimes it works out to be positive, sometimes it works out to be negative. If it's positive, it means that the angle that you just figured out is an acute angle, less than 90. If it's negative, that just means that the angle that you're about to figure out is going to be an obtuse angle, somewhere between 90 and 100 and 180. Okay, so what you're going to do now is you're going to find cosine, you're going to find what this is. Get your calculators out, figure out what all of that is. But theta itself is now equal to cosine to the -1 of all of this, right? All of that stuff that I just told you about on top there. So once you figure that all out, you can now figure out the inverse cosine of that number to get your angle. I suspect it's going to be a negative answer, which means that, and in this case, I know when I was teaching my advanced functions class, I said you never put a negative number when you're trying to find cosine to the -1. And I'm going to make an exception here for when you're doing this. If it's a negative number, the calculator will, in fact, or should, just give you an obtuse angle. So could you go ahead and tell me what that angle is, please? What is the, actually, this one should be acute. No, it should be acute because it looks like this angle right here. So it should be acute. All right, so this number here should actually be positive. Can I get you to work that out for me now, please, as quickly as you can so we can move on to the second way that we're going to approach the same question, right? Some of you might like the second way better. Some of you might say, no, I'm going to stick with the first way. That's your call. But I will tell you that once the questions get more and more complicated, the second way that we're going to do this makes a lot more sense. Okay, I find it much easier when you're doing it the second way, which we'll get to in a minute. Can I get you to give me that answer, please? What angle am I looking at? So the cosine to the -1 of all of that stuff that's inside of that. 38.67. Is it only Sarah that's working for us today? Is everybody lost their calculator? 38.6. So it's 38.6 from the 300 Newton force. And can I get, okay, Carly says she got the same. And did anybody else try this for themselves? Or are you just sitting there looking blankly at the screen? It's important. Thank you, Ashlan. Thank you, Tash. Okay, good. Okay, so that's method one. And we've done that before. And by the way, the last time we did that, we used the sine law to do it. Yes, you can use the sine law still if that's what you want to do. Nothing wrong with the sine law. I personally think the cosine law is a good alternative for when you're looking at a triangle that has all three sides. That's why I did that here. Plus, for one of your homework questions, that's actually useful for you to be able to come up with. Okay, let's move on. Same question, but now we're going to try this using components and show you how that works. This is the thing that I think a lot of you have probably seen in your physics class. So what I'm going to do is I'm going to set up the first vector to be somewhere along the coordinate plane, right? So I'm going to set this first vector here, the 300 Newton vector, as sitting right on the x-axis. So the first one I'm putting right on the x-axis at 300. So this distance here is actually 300. So it's really saying that the components of this vector are 300 and 0. So the y component meaning I haven't moved at all on the y-axis. I've just simply moved along the x-axis, means that I am using 300 as my x component, because that's how far along the x-axis I am, and 0 as my y component. My other vector is 70 degrees away, right? This angle right here is my 70-degree angle. So remember, this one has a 360 magnitude, 360 Newton magnitude. So we need to find the x and y components of this vector. And I'm going to remind you what we did the last time. What we did is, let me just do a little quick erase here. What we did is to find the x component of this 360 vector. Sorry, I'm going to go back to black. The x component, right, of the 360 vector, we took the 360, remember, x component is my cosine, times the cosine of the angle that you're making with the x-axis, so cosine of 70, and the y component, which I'll get from you in a minute, and the y component is equal to the same 360 multiplied by the sine of that 70 degrees. Okay? All right. So I need you now to tell me approximately what that is, and then I'm going to show you what you're going to do with that. All right? So approximately 360 times the cosine of 70. Remember, that's my x component. 360 times the sine of 70 is my y component of that point where that 360 vector landed in my coordinate space. So let's get the cosine one first. What's my x component? Approximately, give me one decimal place. We'll use that as the degree of accuracy for this. So I'd like to see a few more people sort of participating here. So 360 times the cosine of 70 equals what for our x component of the vector, right? So 360 cosine, so 123. Thank you, Jordan, and thank you, Ariana. 123.1 And can I get you, and I hope everybody agrees with that, and can I get you to work out the y component as well, please? As again, I think a lot of you have seen this before in physics. Give me the 360 times, so 338.3, Ariana is saying. 338.3. Okay, so here's what we're saying, right? One vector, right? So let's call this vector 1. I put vector and then I put a subscript of 300 then. That's probably the best way to do it. Has the following x and y components. It has a 300 and 0 as 1. The second vector, which I'll call the 360 vector, right? Its components have an x coordinate of 123.1 and 338.3, right? Where did you get the 300, 360 cosine? Taj is saying, and 360. Okay, all right. So let me take you back again to the previous page when we were, previous page to that too. When we were looking at this thing, we said that to get the horizontal component, we took the length of the vector times the cosine. To get the vertical component, now remember, think of horizontal as being your x component, okay? And think of vertical as being your y component. You take the length of the vector times the sine of the angle. To get the x component, which is the horizontal, take the length of the vector, the magnitude of the vector, and multiply it by the cosine. Just think of cosine as your x and sine as your y. Okay, Taj and Ariana, think of it that way, right? So you, okay, great. And just multiply it by the vector itself that you're working with, and that's going to give you the x and y components of the vector. The x comes from the cosine, the y comes from the sine. Ariana, does that help you out as well? Are you good with that? Okay, good. Okay, let's move forward now. And we're back to here. No, this first vector, we didn't have to do anything because this vector is sitting right on the x-axis. So, I mean, you could use the cosine of 0 and the sine of 0, and you still get the same answer that the x component is 300 and the y component is 0, right? You can try that on your own if you have time. So 300, 0 is, just think of where this point of the vector is. Sitting on the x-axis, right? It hasn't rotated yet. It's 300 and 0. The second vector, and you think of it as being the coordinates of this vector. The x-coordinate is 123.1 and the y-coordinate is 338.3 according to what you just gave me. Now, I want to add these vectors together. That's my purpose right now, to add these two vectors together. Well, if you remember when we were adding vectors together and had the components of the vector in R2 and in R3, right? We just simply added together all the x's and added together all the y's, and if it was in 3 space, we added together all the z's as well. So we're going to go ahead and add together all of the x components, because that's our goal here, to sum two vectors together. If we have the components, we can just add the components together. So I'm getting 423.1 as the x part of that. And this is easy because that's just adding to 0. And 338.3. So my final, if I were to draw the vector on here that represents some of these two vectors, it would be some vector over here, which has the x's added together and the y's added together, right? And the x and the y's would have these two coordinates. Can you go over that? Ariana says, I sure can. All I'm doing here, if you think back, Ariana, to when we were doing 2 space and 3 space, and we had vectors and their components, like the position vectors, think back to those position vectors. So if the two position vectors had an I component and a J component, we just added all the I's and added all the J's. Remember that when we're doing the 3 space? Where did the 423 come from? Did I add it up wrong? I'm just adding the two x's together, the 300 plus the 123.1. I'm just adding the x's together. I'm adding the y's together as well. Okay? So you made me kind of get nervous there. I thought I might have done something wrong. I've already messed up with the test majorly in some ways. Anyway, so here is the final vector. This is like a position vector as well. Think back to 2 space now. Here's my position vector, which has these components, 423.1 and 338.3. So this vector represents the vector sum of the V300 plus the V360, right? That's what this represents. That's what these two components represent. Do you remember how we got the magnitude of a vector if we had its components? Think back again to R2, right? What is the magnitude of this vector? The vector has the components 423.1 and 338.3. Does anybody remember how we find the magnitude? So I'm trying to find the magnitude of this vector, right? Does anybody remember how we did that? Does anybody? So I have the two components, 423.1, distance formula. Thank you, Richard. And to get the actual magnitude, we're just going to simply take the square root of the sum of the 423.1 squared plus the 338.3 squared. So this is going to be the sum of the 300 Newton vector and the 360 Newton vector. That's all we need to do. So this is the sum. In fact, in fact, I had it up here. The sum, I shouldn't put these lines around here because I haven't gotten to the sum yet. So let me take out these lines around the side here, but I will put the lines around the second one. So the sum of the V300 plus the V360. Okay, so that's your, thank you, Richard. That's your task right now. For the x component squared plus the y component squared, and then we square root everything. Can I get you to do that for me right now, please? What would that look like if you were to calculate it? So you have your calculators there. Go ahead and do that now, please, everybody. When you have an answer, let me know. And it's an approximate answer, obviously. All of these should be approximate, except the first one. Okay, folks, those calculator fingers should be working overtime right now. And we should have a number in that chat very soon. 541.7, I'm hearing. That's, of course, in newtons. Does that number look familiar? Does that number look like something we've seen before? Thank you, Sarah. Thank you, Carly, Ashvan, and Alexander. All right. Have we seen that answer before? Well, let me take you back a second. Let me take you back to the page before this. Look at that, 541.7. So we have seen that answer before, but we didn't use components to do it. We just used a parallelogram law to do it. Okay, but what about the other part, which is the direction relative to the 300 Newton vector? So I want you to think now, right? Let me draw a little diagram over here. Here's an angle that we're trying to find inside here, right? We have some coordinates up here, right? And I'll just remind you what the coordinates are. There are x and y. So 423.1, 338.3. Oh, geez, I forgot already. 423.1, 423. That doesn't look like anything. Hang on. Let me fix that. Let me fix that. Let me fix that. So 423.1 and 338.3. 338.3. Okay, and what I'm trying to find is this angle inside here. Let me remind you now, we know that the x part of this would be the same as this distance along the x-axis. So the 423.1, this is 423.1 right here. This distance going up is the same as the y-coordinate, so 338.3. Right? What I'm trying to find is this theta right here, because that theta is how far I am from that 300 Newton line, isn't it? All right. So how would I find that? Using SOHCAHTOA. All right. Look at the triangle I just drew. There's a right angle right here. Right. And I'm trying to find theta. What would you suggest I do to find my theta? Just think SOHCAHTOA, folks. This is trigonometry. A lot of vectors is trick. If you didn't like trigonometry, you're not gonna like vectors. Okay. Tan. Thank you, Ashvan. So we're gonna use tan. We're gonna say that the tan. This is the magnitude. This is the direction part of it now. That the tan of theta. Now, what should we put over what? Which side should we put over which side? Is it the x over the y or the y over the x? Which one makes sense to you? right? What should it, and it is, by the way, Ashwan, always going to be that. We're going to put the y component over the x component. So the y component here was the 338.3 over the x component, which is the 423.1. So theta should be equal to tan to the minus 1 of 338.3 over 423.1. Okay? Jordan and Ashfan are both right. Thank you, Jordan. Thank you, Ashfan. So what I want you to do now is quickly figure out what that angle is, because that's the angle that is the distance, or sorry, the angle away from the 300 Newton line, going towards our resultant vector, right? We put the 300 Newton line up against the x-axis, and then we said that the resulting vector that we got would be that one that had those components, and therefore that angle that you form from putting the y over the x of the components should give me the angle that I'm trying to find. So folks, can you help me out? What's that angle? And I've only seen some people over and over and over, but I haven't seen everybody. There's lots of people. 38.6 is what. Thank you very much. Degrees. Now that answer, again, should look familiar, right? So this is 38 degrees from the 300 Newton vector, right? Well, have we seen that before? Turns out that we have. Right? Again, it's a completely different way. We use a cosine law. In fact, we use a cosine law twice to get this answer. But we got the same answer. So the beauty of math, and I keep saying this, is that you have different routes of ending up at the same place. Is it coincidental that we have to use these numbers? Of course not. You could have used any numbers and you would have still got the same result. Okay, now you're wondering, I think I like to use the parallelogram law to do this. That seems more, so I've done that a couple of times. That makes sense. But what if, all right, let's go to this example. What if we had three forces that we had to play with, right? I can tell you right now, there is no way that I am going to try to do this using the parallelogram law. I wouldn't, and I wouldn't suggest you do either, all right? So look at this one. William, Caleb, and Kristen are playing tug of war in which they're each pulling on ropes tied to an object with different amounts of force in different directions. And they give you the magnitudes of 300, 240, and 180, respectively. So William is at a 38-degree angle counterclockwise from Caleb, and Kristen's force is applied at a 74-degree angle clockwise from Caleb. Assuming no friction, what's the magnitude of the resultant force from them all of them pulling together? So I've got a little diagram here, right? And I just realized I have to change up my diagram a little bit because I really should have put one of these forces. Let me see if I can do this easily now. Somewhere down here. And this one, and you'll see, hopefully see why in a minute. I'm not drawing them to scale, so please don't give me a hard time about that. So Williams' force is applied at 38, let me go back. So the magnitudes of the force are 300, 240, and 180. Williams' force is applied at 38 degrees counterclockwise from Caleb. Let's use this as Caleb, right? I'll put a C on the end of Caleb and say that's what Caleb is. So this angle inside here is the force that we're saying is William, and that's 38 degrees going in a counterclockwise direction. 38 degrees going this way. And this force, oh, by the way, Caleb's force, we'll get to that, Caleb's, the magnitude in a little while. The other force is Kristen. So this is William, by the way. The other force is Kristen, and Kristen is with 74 degrees clockwise from Caleb. So here's Caleb right here. So it's 74 degrees going this way. Okay? All right, hopefully I haven't left anybody behind so far. And by the way, I'm going to put K for Kristen. Now, the relevant numbers I'm going to put on these are 300 for, who is this now? 300 for Caleb. Let me just make sure it's in the right order. Oh, no, I don't have it in the right order, actually. William is the one who is 300. William is 300. So this is 300 here. And I'm going to try to put this a little bit more drawn to scale in a minute. So William is 300. Caleb is the second one who is 240. So this is two. Actually, you know what? I'm going to put a different color for that. Let's change the color. All right, so putting the actual forces in different colors here. So imagine that they're all three pulling together to get to see which direction. Let's see where they're going to finally end up and what kind of overall force they're pulling with. All right, let me get this right now. So 300, 240, and 180. 300 is William, so that's 300 here. Caleb is 240, so that's 240 here. And Kristen, the last one, is 180. Now, I may not be able to finish this question because I definitely have so much to do that I think if I start it off, that most of you can finish this on your own. But let's just keep going anyway. All right, so this is definitely not drawn to scale, as you can see. How can I make this look a little bit more drawn to scale? Let's see if I can make this a little shorter. Yeah, and let's make this one a little bit longer. So it looks a little bit more drawn to scale. All right. So this is the longest one. This is the middle one. This is the shortest one. All right. So let me make sure I got all my numbers in the right place here. Let me make sure I got all my numbers there. So 300 newtons is William. This one here. 240 is Caleb. And 180 is Kristen down here. And they're all in newtons. I'm not putting the N for newtons. Let's just assume that it's newtons. Okay. Now, assuming no friction, what's the magnitude of the resultant force from all three of them pulling together? What we're going to try to do is to get X and Y components for each one of these, right? And I hope that this is going to make sense to you. We're going to put Caleb first, right? We're going to put William second. There's no particular reason for doing it this way. And we're going to put Kristen as the last one. Right? Using a table, I think, is a useful way to kind of organize your information. Now, think of Caleb as sitting right on the x-axis, right? That's where Caleb is going to be. So we chose Caleb. And by the way, and this is consistent with what the question says, William is 38 degrees clockwise. So William is the one that's up here, 300 degrees away in a counterclockwise direction from Caleb, whereas Kristen is in a clockwise direction from Caleb, and she is 74 degrees clockwise. So that's where Caleb is. Okay. So if Caleb is sitting on the x-axis, right, how can we find Caleb's, can you give me Caleb's x and y coordinates? So where is the tip, right? What would be the coordinates of that tip right there? Come on, folks, I need your involvement now. What are the coordinates of that tip? Right, give me x and give me y coordinates for the tip of where Caleb is sitting right there on the x-axis. So he's 0 degrees away from the x-axis. What would you consider to be his coordinates? So 240, 0. Thank you, Sarah. Sarah is consistently right there with us on this. So 240, 0. Is there anyone who isn't sure where that came from? Because I don't mind stopping and going over it to be so that everybody is clear on that, right? Clearly Sarah knows, but is everybody else okay with 240 and 0? If I'm using that as sitting right on the x-axis, right? I don't see anybody coming up and saying they didn't get it, so I'm going to move along. No. Oh, I'm doing that wrong. It's 240 and then 0 over here. We have x and y separately, so let me change that. So 240 for the x and 0 for the y. Okay? Now, to get the William component, William is up here, 38 degrees, and I'm going to ask you to consider this rotation to be a positive rotation. 38 degrees going in a counterclockwise direction. So what would that look like on a grid in terms of the x part of that? And I'm not going to say anything. I'm just going to ask you to tell me, right? I remember it's 300 newtons long. That's the thing. That's the length of the vector. How would I find the x part of that? So in other words, the horizontal part of that. I'm going to be multiplying two things. What am I multiplying to get that? Come on, folks. Not just Sarah now. Right? Sarah can't carry the load for the whole class. How do I get the horizontal component of that 300 Newton force 38 degrees away from the horizontal line? Right? What am I going to multiply? I'm going to give you a hint. I'm going to multiply two things to get that, right? That horizontal component. We don't have a lot of time here, folks. I need one of you to step up and tell me what that is. Think back to what we just did a few minutes ago with the three people, or sorry, the two people that were pulling the rope, right? What would that X component look like? This is not the kind of reaction I was looking for. Okay, so 300 cosine of 38 degrees. That's your X component. Thank you very much, Sarah. Thank you, Taj. All right. Okay, so it's going to be the 300, no, not 300, sorry. Yeah, 300. It's going to be 300, because that's the magnitude of the vector, times the cosine of the angle, which is 38 degrees. And since I want to move this process along, I'm going to move over now to the y. And so that's going to be equal to the cosine, sorry, 300 again. Folks, if you're not following this, you need to let me know, right? When I ask for input and I don't get any input, it suggests that there are people who are not following. But if you're not following and you're not saying anything, then I can't tell that you're not following. But let me just keep going here. So that'd be 300, but now it's going to be times the sine of the angle 38. Okay? So this is SOHCAHTOA, right? It is Ashvan, it is SOHCAHTOA, but there's a kind of an understanding, like I said, let me go back a couple of pages here. There's kind of an understanding. If you want to get the horizontal component, you multiply the length or the magnitude of the vector times the cosine of the angle that it forms with the x-axis. It is SOHCAHTOA, okay? And that for the vertical component, we take it times the sine. Vertical, think of it as being your y component. Always just remember, cosine is your x, sine is your y. Think of it that way. Sine meaning when I say vertical, I'm talking about along the y-axis, horizontal meaning along the x-axis. Okay? All right, let's go back to this. Now, here's a part that's going to be a little bit tricky. How do I do the one that's going 74 degrees away from Caleb, but in a clockwise direction? What angle should I be using for that? Does anybody know? Right? I'm trying to find Kristen's position. Right? And I'm going to give you a clue to this. Kristen's position should be a negative on, well, it should be positive on the x-axis, but should be negative on the y-axis, because I'm on the, if you think of this as being a coordinate plane, right, then I'm going to be on the negative side of the y-axis if I'm down there. So what angle am I going to be using this time, right? What do you think the angle should be if I'm going to be 74 degrees away from the horizontal line, but going in a clockwise direction? Who can tell me what that angle is and how would you get that angle? All right, 74 degrees away in the fourth quadrant is basically what I'm saying. Right? Nobody knows what that number is. All right, let's do it this way. All right, I need to get to down here, 74 degrees away, but I need to start by going from here in a positive direction and then ending up right there. All right, that's what I need to figure out. What is the size of that angle? I have to measure it from, so 286 Ariana says, and Ashman says the same thing. And that's because what they both did is they took 360 and minus that 74 from it. All right, does everybody see what it is in fact 286? All right, hopefully that makes sense to you because I'm going to put that in. So that's the 180 multiplied by the cosine of that 286. And then for the y component, I'm going to take the 180 and multiply that by the sine of the 286 degrees. Why we're using 286, Tashes? Look at the diagram I just drew for you, Taj. I'm going to put a little rectangle around it. Right? I need to be 74 degrees in the fourth quadrant. Right? 74 degrees away from the x-axis. And thank you for asking, by the way, Taj. At least that tells me that you are trying to understand this. If I'm 74 degrees away, but I have to start off, I have to get to it by going in a clockwise direction, in a counterclockwise direction. So look at the green line, right? That is starting off at x and going around in a counterclockwise direction, getting to this point that's 74 degrees away. Well, it means that I haven't quite made it back up to the 360. I'm short by 74 degrees. So I haven't quite made it up to the 360 full circle. So for me to stop right here, 74 degrees away, I'm going to take that 360 that I didn't quite get to and take off that 74. Does that make sense, Taj? How we got that 286 now? If it doesn't, I can try to put it a different way. But does that make sense? Yes. But how do you know it's in the fourth quadrant again? Well, look back at what the question said. The question said that Kristen is 74 degrees clockwise from Caleb. So it's a choice that we made. We put Caleb in the middle, right? Because Caleb is in fact middle between both of them. And we put Caleb sitting right on the x-axis. So Caleb is 0 degrees away from the x-axis. Okay, Taj? So if I want to get 74 degrees, but not going in a clockwise direction, but sorry, I keep saying clockwise, not going in a counterclockwise direction, which means positive. I want to go in a counterclockwise. Okay, let me back up again. Instead of me going this way, I'm actually going this way to get that 74 degrees because it says in the question that Kristen is 74 degrees clockwise from Caleb. So if Caleb is sitting here, then to get to that 74-degree angle, I'm going down here, which is the fourth quadrant. Does that make sense, Taj, that I'm in the fourth quadrant now? Okay, so, but I have to measure that when I'm putting this together in my table as being an angle measured in a counterclockwise direction. I think I said it right this time, in a counterclockwise direction. So for me to get to down to the fourth quadrant, but going counterclockwise, I'm going to be doing what I have in this diagram here. I'm going to be going from straight through the first quadrant, which is 90, straight through 180, straight through 270. I'm going to get up to this point, which is 74 degrees away from 360. So I just simply take 360 and minus that 74. All right. So apart from Taj, who stepped up and asked the question, I hope that everybody else followed that because I don't mind spending more time on it if you didn't. Okay. All right. So what we have here is all of the pieces of the puzzle. We need to take the x components and add them together. We take the y components and add them together. So I'm going to be asking you now with your calculator. It's not just Taj, it's not just Ariane, it's not just Ashvan, right? It's not just those people, right? And Sarah, it's everybody who should be using their calculators now. I mean, yeah, there will be a test on all of this at the end of the week, and I want to make sure everybody is following along here. So you stop me if it's not making sense, right? Go ahead now. Take 240 plus 300 cosine 38 plus 180 cosine 286. Understand that you're going to get a negative value for your sine of 286, and that's fine. Doesn't matter. What we're ending up with is the components of where the final vector is going to land when we add all of these different components together. Okay, so 240 plus 300 cosine 38 plus 180 cosine 286 is going to give me my new x. 0 plus 300 sine 38 plus 180 sine 286 is going to give me my new y. So 526.0, let's put 02. It's approximately 526.02. And Jessica is busy working on, and by the way, everybody should be confirming that Alexander's numbers are right because I'm not doing it myself. I'm asking you to do it. And we're just waiting on Jessica now to give us her number. And I'm still calling out for Carly. Yes, I can confirm. Thank you, Taj. I'm still calling out for Carly. Carly, we've been calling for you for the past few minutes. Agreed with Alexander. Thank you, Kushi. Jessica, 68.244. All right, so I'll be consistent here. 68.24. Okay, so where do you think we're going to go next? The question was, right, now that we have these numbers, what's the magnitude of the resultant force from all three pulling? Once we have the sum of the x's and the sum of the y's, it's now easy. The magnitude of the result, so let's use this. Let's use c vector plus w vector plus k vector. Let's write it down that way. C plus w plus k is going to be equal to the square root of, using the numbers that we just got. Oh, okay, hold on. Oh, is Alexander, is that number supposed to be Oh, okay. So we're getting a different answer here from what, okay, not, this is not what Jessica is telling us. Okay, so I'm not sure then. There are three people saying 11.67. Jessica, did you check that your calculator was in degrees? I'm not saying you're wrong. You put the only one that's right. I don't know. I'm just going on what people are saying. So and Kushi is agreeing with 11.67. Jessica, you want to just double check your numbers again, please? So 300 sine 38 and 180 sine 286. And let me know whether you want to stick with what you got because we're about to work out the magnitude. And obviously, we need to have the right numbers there. So, Jessica, can you just double check your answers for me, please? I don't want to change it unless you're certain that maybe you might have made a mistake, which we all do, by the way. So, Jessica, just double check for me, please. And then tell me what you're getting. Okay, so it is 11 point. Okay, so 11.67. I'll change that then. And that's okay, Jessica. 11.67. All right, so we'll keep two decimal places all along. All right, so the magnitude of this will be 526.02 squared plus 11.67 squared summed and square rooted. Carly, are you with us now? Right, you just checked in a few minutes ago. Can you work that out for us, please? And of course, everybody else will be checking for themselves as well. So take the square root of the 526.02 squared plus 11.67 squared and tell us what you are getting as your answer. Again, it's going to be approximate because we're rounding all the way as we go along. So please go ahead, Carly, tell us what that number is. And everybody else, if you could double check what you get on your calculator, because, like Jessica made an error. I've made errors before. So let's hear what Carly has and let's see if the class can get behind Carly's answer. Go ahead, please. When you have an answer, just put that into the chat for us. And I can see that we are not going to get this done. But, as I said, it's not, for me, it's more important that we are understanding what we're doing. And that's why I like getting the questions and I like getting all of the input. What does the dot above the equal sign mean? It means approximate. So if you put equal, it means that it's exactly equal. But because we're rounding our answers, technically we should have that dot there to means approximately equal to. All right. So Carly says 526.15. 526.15. Okay, so it means it's not much different from the Okay, I'll take your word for it. All right. Is everybody getting the same thing as Carly? Square root of same? Okay. All right. So 526.2 approximately. And that's in newtons as well. Right? So that would represent the force of the vector, and then we should now calculate the. So was it? Oh, it just asked for the magnitude of the resulting force of the three of them pulling. I'm just going to move on because we're so short of time that I think we need to move on here. So 526.2 newtons. If I did need to get the direction, again, I say that the tan of theta would be equal to the y over the x, 11.67 over the 526.02, and you can do this on your own time. Whatever answer you get will be the angle from the middle person who was Caleb. Right? That's how far you are from Caleb. Right? Going in either clockwise or counterclockwise, depending on how that worked out. I don't know how it's going to work out, but I'm going to move on from there.